45 millimeter mercury. Here should be lower. What is that? 40 millimeter of mercury. So pressure carbon dioxide inside is 40. Pressure carbon dioxide in the blood is 45. How much difference? Only 5 millimeter, right? But that is enough to move the oxygen. So 5 millimeter pressure difference will move the carbon dioxide from here to here. 64 millimeter pressure difference will move the oxygen from here to here.
Are we going to need to know all those numbers?
Yes, these are important numbers. Okay. Now the question is, why for oxygen you need 64, for carbon dioxide you need only what? 5 millimeter, right? Why for carbon dioxide you need less pressure to move? Same amount or volume move oxygen and carbon dioxide. The reason is that membrane through which, this is the respiratory membrane, through which the gas exchange occurs, is more permeable to carbon dioxide than oxygen. So carbon dioxide is more permeable, easily can go. So a small amount of pressure can move same amount of carbon dioxide. Make sense? Less permeable for oxygen. 20 times. See this membrane through which the gas exchange occurs, 20 times more permeable for carbon dioxide than oxygen. That's why the difference. You see here, I explained all this to you already. I also showed what happens in the lung, alveoli, what happens in the tissue. So the tissue, that is the lung. So this is external respiration, this is internal respiration. You see, deoxygenated blood goes to the lung, get oxygen and give carbon dioxide, and oxygenated blood gets back into the heart, then left ventricle sends the blood to the body, to the tissue. So tissue gets oxygen and gives carbon dioxide back to the blood. Ventilation, perfusion, coupling. This is something important. Look at me. I will give you two situations. You tell me which is more efficient, okay? So I am inhaling the air in, okay, from outside. And heart at the same time sends blood to the lung. This is one situation. I am taking air in, air is inside the lung, getting in, and heart is sending blood to the lung at the same time, okay? Another is, I have expelled the air out, and heart is sending blood to the lung. So which one is more efficient? First one. Because when you take the air inside the lung, lung is filled with air, right, oxygen, heart is sending blood to the lung. So blood will get more oxygen. After I expire, if heart sends blood to the lung, that is less efficient. Is it clear? So that is called ventilation-perfusion ratio. Ventilation is pulmonary ventilation, breathing, and perfusion is blood flowing in the lung. That is the perfusion. Make sense? Those two things should be coupled, timely manner, timely way, right? That will ensure that blood gets enough oxygen. Transport of oxygen and carbon dioxide. We know that blood transports oxygen and carbon dioxide. You all know that, right? Blood transports gases. How the oxygen is transported by the blood is different then how the carbon dioxide is transported by the blood. So you need to know that. Just know one thing first, that oxygen binds with what? Hemoglobin, right? So 98.5% oxygen transportation occurs by the hemoglobin. So hemoglobin transports most of the oxygen, 98.5%. Only 1.5% is transported by the plasma. Is it clear? Okay. So here you see 98.5% volume of oxygen is transported by the red blood cells. It binds with hemoglobin and transported by the hemoglobin of red blood cells. Only 1.5% is transported by the plasma. Carbon dioxide. Here. Carbon dioxide is transported differently. Only 20% volume of carbon dioxide is transported by the hemoglobin. Hemoglobin also transports carbon dioxide, but what? Only 20%, not 98.5%, okay? So, much less. About 70% carbon dioxide is transported as bicarbonate, in the plasma. How? Look at this. Carbon dioxide enters into the blood, and blood has water, plenty of water, and what happens? They quickly form carbonic acid, H2CO3. Make sense? And then this carbonic acid quickly breaks again into hydrogen and bicarbonate. Okay, so that is the reaction you need to know. Very important reaction. So carbon dioxide enters into the blood. Blood has water. They together form carbonic acid, and quickly it splits into hydrogen ion and bicarbonate. This is called bicarbonate. Carbonic anhydrase, Ca, is a catalyst that quickly breaks this one. Helps to quickly break it. Carbonic anhydrase. Now you tell me, this carbon dioxide is where? Here, right? In bicarbonate. So that's how bicarbonate. So that's how the carbon dioxide is transported in the blood, present in the blood as bicarbonate. How much? 70% volume. Most of the carbon dioxide is transported by the blood as what? Bicarbonate. And 20% binds with hemoglobin, form carbaminohemoglobin, and only 7 to 10% directly transported by the plasma as carbon dioxide. Okay? Dissolved in plasma. So that's how the carbon dioxide is transported by the blood. So now you know how the oxygen is transported, right? And how the carbon dioxide is transported. Okay? And remember, this reaction is reversible reaction. Okay, so both ways, very reversible. It can quickly form carbonic acid and split into carbon dioxide and water, which is important because when carbon dioxide should be released from here, right? Carbon dioxide should be released from here. The reaction should be opposite. Make sense? So carbon dioxide will get free. So that's why it is a reversible, quickly reversible reaction. Is it clear? So Now, you know, carbon dioxide goes from the tissue to the lung, as this form. Then in the lung, what will happen? Quickly, it will release the carbon dioxide into the lung. Is it clear? Should be released into the lung. Okay, so before we go to next thing, just know, don't need to know detail of this, just know that oxygen binds with hemoglobin, right? Of red blood cell. And hemoglobin transports 98.5% oxygen. So that binding, how much oxygen will bind with the hemoglobin, that can be changed due to a number of factors that can be changed. Important factors that change that binding or saturation. That binding is called saturation, pressure of oxygen, temperature, blood pH, and carbon dioxide. Just know that these 4 factors can change the amount of saturation or binding of oxygen with hemoglobin. Now you tell me, this is very simple one. First one, pressure of oxygen. If oxygen pressure is high, that means more oxygen is there, right? So binding will be more. If oxygen is more, binding will be what? More, high. If carbon dioxide is more, then binding of oxygen will be what? Less, because competition. Carbon dioxide will also try to bind with hemoglobin. So oxygen binding will be less. That is, these 2 things are simple, right? If oxygen is more, binding will be more. If carbon dioxide is more, then carbon dioxide will try to bind with hemoglobin, so less oxygen will be able to bind with. Okay. Temperature. If the temperature increases, binding will be less, saturation will be less. And blood pH. If the pH is more, that means acidic. If the pH is less, that means acidic, and that will cause less binding. So only pressure oxygen, increased pressure oxygen will increase binding, others will decrease the binding. Here you see this curve. This is normal body temperature, so this is normal saturation curve, binding. This way is the pressure, this way is the pressure, this way is the binding. So this is normal. If the temperature increases, the binding will be less. Will move to the right, shift rightwards, okay? Leftward means more binding, rightwards means less binding. So if the temperature goes down, saturation will be more. Increases, saturation is less. Here you see more oxygen, more saturation, more carbon dioxide, less saturation. Okay. This is how the transportation occurs. I have already explained you. This is carbon dioxide entering into the blood. That means from the tissue, carbon dioxide goes to the blood. And carbon dioxide, you see, binds with water that I showed you here. Becomes carbonic acid very quickly, fast. And then forms bicarbonate and hydrogen ion. Okay. And carbon dioxide is now here. Okay. 70% carbon dioxide will be transported as bicarbonate. 20% will bind with hemoglobin and will form carbamino hemoglobin. Will be transported as carbamino hemoglobin. Only 7 to 10% will be dissolved here in plasma. Okay. And the thickness of those arrow-headed lines are showing the volume. So most of the carbon dioxide is forming bicarbonate. Okay. That I showed you here. And when the blood will get back into the lung, you see the reactions are just going in opposite direction. So carbon dioxide will be released, will go to the lung, of the lung. Okay? Very quickly. Hemoglobin will release the carbon dioxide, will go back to the lung. Okay? Plasma, from the plasma, directly carbon dioxide will go to the lung. Okay, so how the respiration or breathing is controlled. In the medulla oblongata and pons, you know those structures in the brain, you have seen those when you did the dissection. So this is the pons and this is the medulla oblongata and then the spinal cord. So this is the pons, this is medulla. In the pons, you have a center that is called pontine. Respiratory center. It makes sense in pons, that's why pontine. In the medulla, you have two centers. Okay? The ventral, this is the front group, and this is called dorsal respiratory group, also called center, but group is more used. So there are three, two in the medulla, ventral and dorsal, and one in the pons. Okay. Now, see how your breathing is being controlled. First thing you tell me, you breathe 24 hours, right? Throughout the life. So do you control or it happens by itself? It's involuntary, right? You don't. You can, if you want, then you will stop for a while, you can do that, right? But normally you don't do. You don't even care, right? You don't even think. Whole day you never think if your breathing is going okay or not, if you are healthy, right? We don't have time to think about all these things that are happening inside the body, right? So how these things are being controlled? Inspiration, you are inhaling air, then at certain point it is getting stopped by itself, right? And then exhalation is occurring by itself, then another cycle, right? So one after another. So involuntary. Who are controlling that? Something, these are the centers, okay? Three centers are controlling your respiratory cycle, inspiration and expiration. Now, this is the lung. Again, this is the lung, and you have pleura around the lung covering. This is the chest wall. Okay. So, pleura, chest wall, and lung tissue. All these structures have receptors. What kind of receptors? Called stretch receptors. Activated by what? Pressure, right? Stretch receptors are present in the pleura, that means covering of the lung, in the chest wall, as well as in the lung tissue itself. Okay. Now, you tell me, when your lung is expanding, more pressure, right? In the wall, in the pleura, in the lung tissue, more pressure. So, the receptors will be activated. Is it clear? Okay. So, the stretch receptors will be activated when lung expands, starts to expand, and will send signal through the nerve to the dorsal respiratory group. So, from the receptors, signal will go to the dorsal respiratory group. So, that is the function of dorsal. receiving the signal from which receptors? Everybody? Stretch receptors. Okay. So more signal will go when lung is expanding more and more. Is it clear? Okay. So it is collecting the signal. What is going on? How much expansion is occurring in the lung? And when the lung has expanded enough expansion has occurred, like normal breathing, dorsal will send signal to the ventral. That lung has already expanded enough. Okay? Dorsal will do what? Send signal to the what? Ventral. Is it clear? We'll tell the ventral respiratory center that lung has already expanded. Okay? It's time to do what? Stop it. Otherwise it will burst. Time to stop. But dorsal can only collect the information, it cannot stop the lung. Is it clear? Dorsal can only collect the information from the stress receptors and give it to ventral. Ventral can do what? Ventral can send signal to the respiratory muscles. So this way, send signal to what? The respiratory muscles, diaphragm and intercostal muscles. And tell them to stop contraction. Tell the muscles to stop. Now relax, okay? So when the muscles, those two muscles, particularly intercostal and diaphragm, will stop contraction, will relax, then what will happen? Recoiling of the lung will occur. Make sense? Expiration. So that is happening all the time, 24 hours throughout the life, okay? Continuously they are working. Your lung is expanding. Which receptors are getting activated? Stretch receptors, right? Sending signal to what? Dorsal. So dorsal is telling ventral that lung has expanded enough, okay? It's time to stop it. So to stop the expansion of the lung, ventral sends signal to the muscles, respiratory muscles. Make sense?